All right, peeps, here we go. We're going to jump into a video dedicated to understanding some of the general pieces of the graphs of quadratic functions. So we're going to look at the pictures of what functions that fall under this family right here look like. So the general form of a quadratic function is y equals ax squared plus bx plus c. You've seen that form before if you've watched earlier videos and have done factoring. Now it's time for us to graph this stuff. A, b, and c are constant numbers. They can be fractions, they can be integers, they're going to be any rational numbers. So let's dive into this. So first things first, we're going to end up graphing this stuff out very particularly and end up being able to get to a point where we don't have to graph out tons and tons of points. But let's first learn about the anatomy of these graphs. So first thing is to understand what the importance of this point is right here. That point, and I'll put a dot right there, is known as the vertex. The vertex is either the highest value on the graph. In this case, it's a maximum. That's what we call that vertex when it's the highest point on the graph of A. Here's a big word, parabola. And a parabola is that U shape. That's the name that we give to that U-shaped graph. So that point, that highest point, is a maximum because it's the highest point. We'll get to a minimum on the very next slide. What is the vertex? Well, that vertex again is that highest point. It also happens right along the center of the shape, and that center, or the fold, is called the axis of symmetry, and we'll talk about that one shortly too. But for now, the vertex, in this case, is equal to the point 1, 2. And so that is a maximum in this case. It's not always a maximum, but in this case, it is a maximum. All right, now I briefly mentioned that there's this axis of symmetry, and I'm going to call that AOS normally, but for right now, I'll just say axis of symmetry. I'll say axis of symmetry and spell it out. Normally, I call it an AOS. That is the vertical line that splits a parabola into two symmetric parts. Like if we were to fold this side over onto that side, it would fold perfectly, assuming that I drew it perfectly. And it's going to be the vertical line x equals 1 in this case. Notice that the x value of the vertex is the same as the x value of the axis of symmetry, which makes sense, because the axis of symmetry goes right through the vertex. That's it. So again, introducing you to what the vertex is, that it's a maximum here, and that we have this thing called an axis of symmetry. All right, let's get on to another example of a quadratic function. Here we have one where the vertex was meant to be right there. So I'll put it right there, and we'll draw in the axis of symmetry. Remember that axis of symmetry is the fold that splits this thing into two equal halves. So let's talk about what the vertex is. So the vertex, in this case, is the lowest point on the parabola. That is at the point -4, -3. So your vertex is -4, -3. Not so bad. And this is known as a minimum, again, because it's the lowest point. This vocab's not hard to remember, right? Minimum, lowest value or least value. And so now we also know the axis of symmetry goes right through the x value of the vertex because it splits the parabola into two equal halves. So I'll call that the AOS this time, as I talked about in the previous slide. So the AOS is x equals -4. Sweet. So notice that this parabola is facing up. And when you're facing up, you'll have a minimum. And as we saw in the previous slide, when you're facing down, you have a maximum. Sweet stuff. All right, we're going to keep rolling into our generic understanding of parabolas. And we're going to just look at parabolas that are of the form ax squared. Hopefully you can see that 2 in the screen there. So, it really, honestly, it could work for y equals ax squared plus bx plus c. But I'm looking at all formulas that are just centered right here at the origin. So what we're about to generalize is what happens when we change the value of this a term. That's what we're focusing on now. So let's see. We've got y equals 1/2 x squared, and I've generated that graph right here and put it there. We see that it's facing up. There's one other graph where the a value is greater than 0, and it faces up as well. So I'm just going to kind of mention that the a value, it's the leading coefficient. Remember the coefficient, or any coefficient, is a number multiplied by a variable. So that's 2 in this case and 1/2 in that case. In both those cases, 1/2 and 2 are greater than 0. And the parabolas are facing up. Now let's look down at these two parabolas. we have that a is less than 0 here. Negative 2 is less than 0. And here a is less than 0. And what we notice is that the parabola is face down. So that's something you could memorize, and I want you to, but I also want you to understand it. So if you look at a being greater than 0, what's happening here is we would plug in numbers for x and square them. That makes positive numbers. And if I multiply a positive number by another positive number, all my y values that I'm getting out would be positive. Nice. And here the same thing happens. So we end up facing upwards. So when you have a positive a value, the graph faces up. The graph of a parabola, that is, faces up. Now, what about when a is less than 0? Well, it's the opposite of when a is greater than 0, so we would expect the graph to face down, which makes sense because when we square a number, it's positive or 0. And then when we multiply by a negative number, we would get a y value out that's either 0 or negative. And here we see all y values that are 0 or negative, and the same story here. So when the leading coefficient, or a, is less than 0, when it's negative, the graphs face down. Yet there's more to get from these pictures here. The other thing I'd like you to notice is when we have a value in size, so not necessarily positive or negative, but how big the number is, 1/2, negative 1/6. They're both pretty tiny numbers. We notice that the graphs are wider than the graphs where our coefficients are bigger. The 2x squared graphs are pretty steep. They rise much quicker in the window than the 1/2 and the 1/6 do. Why is that? Well, again, it comes from the order of operations and what happens when we multiply by these numbers. So I get the parabola shape from x squared, but then I multiply every one of the values I get out by 1/2. So imagine you got out a number like 4, and now all of a sudden it's 2. So if you plugged in 2, you get 2 squared is 4, but then you divide it by 2, and it brings the numbers down. It makes you go up slower. The same thing by the 1/6. We're going down, but we're going to go down much slower than if it was just minus x squared, because you're taking a sixth of whatever number that is, causing the graph to be wider. The opposite happens the bigger the number gets. The bigger this coefficient is, 2, 4, 17, negative 17, the steeper this graph is going to be, because we're getting out a number for x squared. Let's say you plug in 1. 1 squared is 1. But then you're doubling it. So then it rises the y value up by double what it would have been, making the graph steeper in either the negative direction or positive direction. So to generalize, when a is more than 0, the graph faces up. When it's less than 0, the graph faces down. We went over y earlier in this segment. And when the a value is smaller, positive or negative, the graph's pretty wide because it goes up or down slowly. The bigger the a value gets, the faster that graph goes up or down, making it more narrow. Cool. Oh, but we have a little bit more. We're going to basically now test our skills based on what we just went over, and that's the whole purpose of this. We should be able to generalize what the graph looks like without having to graph it out, and that is going to save you oodles of time in your math career. So, I'm not going to define what that oodles is, but let's jump into this. So the instructions here, I didn't write them up here, so I'm just going to tell you. I would like you to go through each of these functions and determine roughly what the graph will look like. Is it going to be wide or narrow? Will it face up or down? So if you want, you can pause the video now and give that one a roll. And hopefully you paused the video. If you didn't, that was an awkward pause. Okay, so here we go. Y equals 6x squared. 6 is a pretty big number. So this graph is going to be pretty narrow. So I'll say it's going to go up very quickly, and it's going to face up. Sweet. So I don't know, something like that. Pretty narrow and facing up. Y equals negative 20x squared. Well, it's negative, so we know it's going to face down, right? So that thing is facing down. And that 20 is huge, so it's going to be super narrow. I can't even draw it narrower than I drew the 6x squared. It's going to be even faster than 6x squared and facing down. Okay, I guess I'll put narrow. Nar for short. Negative 3/4 x squared. We know it's going to face down, but the 3/4 is going to make it wider. So it's going to be wider and facing down. So I'll say wide, facing down. And then 1/3 x squared. Well, it's a positive a value, so we know we're facing up, so we'll say face up. And since it's, well, 1/3, it's a relatively small number, it's going to be wide. So it's facing up and it's pretty wide. That's it, peeps. Vertex axis of symmetry, which way the graph is facing, and how steep the graphs are. Very important concepts to understand about parabolas, which are the visual representations of quadratic equations. Sweet.